Hello folks, in this video, I'm going to explore how we can leverage a machine learning tactic called adversarial perturbations. Adversarial perturbations. Initially, it didn't roll out of my tongue, but I kept on practicing it to be able to pronounce it. And I'm still not sure if I'm pronouncing it right. So we're going to explore adversarial perturbations machine learning technique to prevent images from being deepfaked. Now, I'm sure that many of you are aware of news and incidents happening around the world where student images are being deepfaked and they're being edited to look like they were somewhere they weren't or doing something they never do. And this has affected a bunch of schools, and it has resulted in the schools being extorted for cryptocurrencies or money or Bitcoin, something like that, and it's caused some panic. So it got me wondering how, from a technical standpoint, besides policies and procedures and letting people know and knowledge sharing, how we can do it from if there is anything that we can do from a technical standpoint. And that's how I came across this machine learning technique called adversarial perturbations. Now, to be honest, this was way beyond my comprehension. It required a lot of machine learning knowledge, a lot of AI knowledge, perhaps even deep learning, neural networks, and all that stuff. And I'm new to all of it, but with the help of ChatGPT and Gen AI, I was able to understand bits and pieces of this and put something together and develop something in terms of like a prototype. So this is a video that will kind of take you through that journey on how you could potentially leverage machine learning now and maybe in the future to prevent such incidents from happening. So, like, we already know what deepfakes are and why we should be concerned. I'm going to talk about, from a high level, how the adversarial perturbations or these open source tools work. By the way, these are some open source projects that you can find in GitHub, and you can download the repository and spin your own version, make changes and things like that. So with ChatGPT to find how I can fix it, and I eventually fixed it. This has many components to it, a lot of machine learning components to it. So it may not be easy for somebody who's just starting with Python or who's not tried Python coding, Colab coding, machine learning coding. It may not be easy, but I wasn't too experienced. But with the help of ChatGPT, I was able to understand some basics, and it gave me a little bit of confidence to explore complex projects, or rather complex machine learning projects. So I will just give you a brief overview of what we are doing here. And by brief, I mean it's very brief. I'm not going to go into the deep knowledge of how all these works. To be honest, I'm still not sure how all of this works. This is still experimental, and this is I'm dabbling. I'm still dabbling. Okay, that's the best way to put this. So here what I'm doing is I'm connecting it to my Google Drive folder where all the code and the folder which contains the photo is all there. Then I'm trying to import a bunch of libraries that I need, like PyTorch, Torch Vision, OpenCV, Matplotlib. Not sure if I said that correctly. If you machine learning specialists know anything, please add to the comments. if I'm saying something wrong. Um, and NumPy is popular. It's popular statistical numerical Python library. PyTorch, by the way, is the framework that handles all the numerical computations of the images on a GPU. It's what will allow us to manipulate the images at the pixel level. Then you have Torch Vision. It's a part of PyTorch, I think. And what it does is it helps transform the images. OpenCV, it's a popular library for computer vision tasks. We use it to read images from disk, change the color space, like for example VGR to RGB, and save them back to the disk once we applied the perturbations. I also know that OpenCV, they use it for a bunch of object recognition machine learning models, like in the CCTVs, where they are able to identify the objects in the CCTV or the faces in the CCTV. I remember coming across OpenCV library for implementing an object detection model in the CCTV camera systems. Then you have Matplotlib. It's a go-to tool for visualization. It lets you display the images and compare the results and ensure the adversarial changes don't visibly alter the student's photo. Then you got NumPy. It's short for numerical Python. It provides fast and flexible arrays, which PyTorch also uses behind the scenes. It's perfect for handling large amounts of data, like the pixel value in those images. So these are some of the basic models that you have to import. And again, this is a copy and paste of the code that is already there in the open source code that is available on GitHub. Here you're bringing in the ComGAN, I believe. Then we load a couple of other models like ComGAN and SimSwap in this DFRAP project. And ComGAN is basically an adversarial network that focuses on replicating the way social media platforms compresses the images. By applying these real-world compression techniques, ComGAN allows us to see if these perturbations remain effective once an image has been uploaded to platforms like Facebook or Instagram. So the ideal scenario is, let's say I'm the marketing manager for the school. My workflow should be that I apply these perturbations or the DFRAP protection onto the students' images before I upload it to social media. So what ComGAN lets you do is kind of simulate that scenario where once you've applied those perturbations, and if you have uploaded the images to Facebook and Instagram after applying the perturbations, will that protection still stand? That's what I understood from what ComGAN is. Then you have SimSwap. That's another one that you're loading. So we're loading the ComGAN model, and there's a whole bunch of associated code to load that model. Then you're also loading, I believe, something called SimSwap here. SimSwap. On the other hand, it's a face swapping tool that it blends. What it does is it blends one's facial features onto others. So it's unlike old face swap algorithms. SimSwap focuses on preserving both the source identity and the overall facial structure, resulting in highly convincing edits. So that's you're importing those two models here and trying to figure out how we can proceed further. And there's a whole bunch of image to tensor function. There's a whole bunch of code that you have to run. And another thing I wanted to highlight is there is something where you apply the epilepsin, I think. I can't pronounce that word correctly. I think it's called epsilon. I think it's called epsilon. It's called I want to show that here. That is part of the. Okay, it's part of the PhotoGuard. Okay, CUDA is your. I believe it's the GPU driver for NVIDIA GPUs. So you got to import that. If you want to use a GPU, the free GPU units available in Colab, you have to import the CUDA drivers. You got to make sure you switch it to. You got to try and make sure you switch the runtime. Change the runtime type to T4 GPU, otherwise it may not run. Even if this enable a lot of your code that requires high computing power, it may not just run. So yeah, epsilon is what defines the maximum amount of noise that we're allowed to add per pixel. So what we want is we want it to be small enough to be invisible, but large enough to disrupt the AI models. Okay. So in the end, when you run the DFRAP deepfake prevention Google Colab script, you're supposed to get an outcome that is a bad outcome, where the deepfake generation tool gives you an output that is something similar to this one, with an unrecognizable face across the different models that we test that image, which has been added with the noise. So if you look at this one, here we're testing it again against the StarCan model, and this indicates the closer the number is to 0, the more similar the image, the fake image is to the actual original. The further away the number is from 0, the more distorted the image is. Although in this testing, it's kind of hard to determine if it really worked, because the fake image here, which it says is as close as possible to the original image, still doesn't look that great. So it kind of makes me question the efficiency of this particular attack against deepfake models. Then again, it is supposedly better against certain image generation models like ComGAN, SimSwap, and things like that. So if you look at it in a nutshell, that it is kind of working, but if you test it against a stable diffusion model, you will see that it doesn't work. But against these specific models, you might have some luck. But when I initially saw that the final image, when tested with and without the ComGAN meaning the, the, the compression that happens when you upload your image to social media after applying the perturbations, looks like, you know, this is what we want. This is what we want. And this is not the case if you test it against the most advanced stable diffusion model that you can find on Hugging Face. But in theory and in the future, I'm hoping that these tools will end up distorting the image to a point where it's beyond usable as a deepfake. So here you can see that it's testing against different models. Here I'm trying to put this face onto my original face, and with the original SIM swap model, it's able to almost put that image onto mine. But if you look at this one, after applying the noise or the perturbations, that deepfake looks pretty bad. Likewise, with ComGAN, that deepfake looked pretty bad. Even if you look at the first row here, this one looks better, definitely, but still not that great. And that is the original StarGAN. And I think the StarGAN model is the model that applies facial features like beard and mustaches, eyebrows, changes the eyebrows to the original image. And once the perturbation is applied, you can see that, and after the ComGAN compression happens, you can see that the image is completely distorted and unusable. Sorry, without ComGAN and with ComGAN, again, it's unusable. So I was really excited when I initially saw this, hoping that any image that I pass through the DF you know, it would be immune to deepfake, which is not the case. This is, again, like I mentioned, an open source experimental project, and it needs further development. If you look at this one also, this is the actual original image. This is the adversarial image. Now, what is the difference between the original image and the adversarial perturbation image is that it adds the noises, and like I mentioned in the initial part of the video, it doesn't seem that much different, except for the fact that it looks a bit more grainy once the noise is applied. It looks a bit more grainy once the noise is applied, and maybe slightly more pixelated than the original. That is the only difference that I can tell. I've also, to be honest, I've put in a row. I've added to the original image folder in my DFRAP project. I've actually put in a very low resolution image because I was being a bit paranoid. So I used to really try to find that document here. Hold on one second. Yeah, this one. Yeah. I used a really low resolution image, and I've also read that this is more effective when you apply the protection on a high resolution image. So the difference between them both is that it's more grainy, it's more gradienty, and you can change all these elements of how much gradient or noise you want to apply through epsilon, and there is a gradient variable in the code. You can change a whole bunch of those features, but Ideally, what we want to see in the end is when you try to swap a face onto the original image, you want the output to be something as crappy as this. You want it to not work, basically. So this is, in a nutshell, how DFWrap project works. Now I'm going to show you really quick how the PhotoGuard Colab project also works. Then you have the PhotoGuard, which again is an open source project from created by a bunch of MIT researchers, and the link to the GitHub page is here. I'll also post that in the video description. I'll just quickly run through the diffusion attack. There are three options. There are three flavors. One is an encoder attack, an in-painting attack, and the other one a diffusion attack, which is the most advanced among the three, and that requires more compute, more GPU processing than the other two. And if I show you the demo, I was able to replicate this diffusion attack. I was able to make a copy by opening it in Colab and then making a copy and making a few changes. The original code did not work, so I had to make some modifications. Even after making the modifications, it took a really long time to apply the protection because I was running on the free version and the runtime was on a T4 GPU, which is not enough. You need at least a A100 GPU, which I believe is one of those NVIDIA's AI processing GPUs. So you need this, and in order to enable this, you need a paid Colab account. So I couldn't execute this complex diffusion attack using PhotoGuard yet. I'm hoping to try it after I enable my pro account. Or if you have any experience with it, please let me know. Add something in the comments. But just to give you a quick overview of how this works is once you have, this is the original image, the original source image, and once you apply the protection or the adversarial perturbations, the image will look like this, slightly more grainy than this original image, still not bad, but you can see the areas around the cheekbones, the forehead, the chin, it is applied something, it is applied some kind of a gradient effect, slightly more pixelated. So once you apply the protection, this is how the image is going to look like. And using a stable diffusion model, you give a command, you give a prompt like 2 men in a plane hugging. If you did not apply the protection, this is how the outcome would be. This is how the outcome would be if you took the original source image and gave the prompt as 2 men in a plane hugging. This is how you would get the outcome as. It's pretty good. But once you apply the protection, once you apply the adversarial perturbations to this image and you take this and then give the prompt, 2 men in a plane hugging, what happens is you're supposed to get an outcome that looks like this, which is unbelievable and a very bad output and will not pass off as a believable deepfake. So this is how, in a nutshell, the more complex diffusion attack is supposed to work. So In short, how was my experience with adversarial perturbations and deepfake prevention techniques? I must say I've had mixed luck with these strategies. It's not a complete solution, but it's a promising step towards safer online spaces. I'm hoping that ideally major tech companies like Meta, Google, Microsoft, OpenAI will step up to create practical, accessible tools. After all, they are the ones who help build all of this AI technology that is kind of fueling the deepfakes. Or we'll just wait for someone to package these ideas into an expensive, shiny new app, which is probably going to be yet another subscription to your ever growing list of subscriptions for $10,000 a year. That will inevitably add to your school's technology budget. For now, I cannot see a better solution than not posting any of your students' images on school websites, or just not posting any faces on any publicly accessible websites. I just don't see a better way than this. No matter what policies or procedures or awareness campaigns you have, or opt in and opt out for parents you have, I just maybe I'm being overcautious, maybe I'm being very paranoid, but truth be told, I don't think deep down there is a better way to handle this than just not posting any of your uh, children's or students' images online. Thank you for watching the video. I would love to hear what strategies you have tried to safeguard your school photos from being deepfaked, or if you plan on doing something along the same line. Please let me know. Add to the comments your thoughts, your ideas, and I hope we can move towards a future where we can protect the children's images online. Thank you.